Hello, everyone. We are just waiting for the numbers to settle in, and then we'll begin shortly. Okay, thank you, everyone, for waiting in the waiting room. So, happy Tuesday. Today, we are very glad to welcome you to another episode of Paleo Perks. And today, we are joined by Xianyi Liu from Utrecht University in the Netherlands. And today, he will be talking to us about bridging the modern and historical timescales in shallow marine habitat distribution in the Bahamas. So, for those of you who are new or are attending a Paleo Perk seminar after a long time, we'll quickly go over the format of today's seminar. We are having welcome and announcements right now, which will be followed by the talk for 30 to 40 minutes, and then we have moderated question and answer session. Do not forget to send your questions to via chat to the questions at Paleo Perks host, who today is Nina. And then our speaker today has kindly agreed to stay with us for an informal tea time, which is a place where you can talk to the speaker in a more relaxed setting and ask more questions about their research or their life and career, things like that. Uh, so, a bit of housekeeping before we go forward. Paleo Perks values the participation of all folks interested in the paleo sciences. Please remember to abide by our code of conduct during today's seminar. You shouldn't be able to unmute yourself for the duration of the talk, but in case you do, please mute yourself out of respect to our speaker. You can ask questions by chatting to the questions at Paleo Perks host or by using the raise hand function. If you face any technical issues during the Zoom meeting, please reach out to the questions at Paleo Perks host. We have closed captions built into Zoom. Use the CC button to show or hide them. Paleo Perks works on the nomination of outstanding early career researchers, and our speaker pool needs to be more diverse and dynamic. So we please request you to nominate any excellent early career researcher that you know who is doing any research in paleo field. We also collect anonymous weekly feedback. On the information of demographics of our audience, and you're highly encouraged to also answer to that form. And we have a special announcement. The Paleo Perks Committee is looking for two new members to join us by the end of this year. We are specifically looking for people interested in doing social media or funding outreach. But if you are anyone who is willing to devote some time of service to our paleo community, you are welcome to apply. And applications are open till November 10. This is a QR code for the application, and the link to the application will also be dropped in the chat. Okay, now without further ado, getting to our today's speaker, Xianyi Liu. Uh, he did his bachelor's from China University of Geosciences, and then followed by a master's in science from the Imperial College London in UK, followed by a PhD in geochemistry at the University College of London in UK, and currently Xianyi is a postdoc at the Utrecht University in the Netherlands. Shiani, please start your talk.
Okay. Thanks for having me. My name is Xianyi, and thanks Nina. Thanks Pillar Perks, giving me this opportunity to show some of our recent results. I'm from Utrecht University in Netherlands. My name is Xianyi, and today we're going to talk about bridging the modern and historical timescales in shallow marine habitat distributions in the Bahamas. First, we have a lot of shallow marine habitats on the carbonate platform. As we can see, I put four figures over here. They are seagrasses on the top left and algae on the top right. And of course, I have coral reefs on the top on bottom left, and some, of course, oid sandbars on the right. And they are absolutely beautiful places and also very important things. Like the coral reefs, they alone have like 25% of all the fishes, or all the 25% of all the marine species in the world, despite they only colonize like 1% of the ocean. Um, And also, this kind of habitats, they actually are dynamically changing all the time. I take um, uh, the, the research by Westphal in 2022 on the left as an example. It says like, okay, like you don't need to understand what does it mean. Especially we can see a different colors the different colors patches, and they are shrinking and expanding. And this colors basically represents each habitat, and because of any kind of external environmental disturbances like storms or seasonal changes or sea level rising, temperature changes, or some people just dump some more shit in this area and it cause some eutrophication, whatever stuff. They also all gonna change the distribution of the habitats. So it's dynamics. So it's dynamic. So on the right hand side, I showed the picture and this a figure, and this is changes of habitats in 80 years in somewhere in the Bahamas. And both I and the previous people find that the habitats are constantly changing in the area in the shallow marine. So there's a relationship between the habitats and carbonate producer. So carbonate sediments, they are produced by a lot of carbonates. Carbonates are produced by a lot of carbonate producers. For example, the corals. Um, they build up and produce a lot of carbonates. Yeah, everybody knows that. They live in certain habitats. For example, the corals. They just love to live in the coral reefs, right? Or on the which is on the hard ground. So there's a link between the habitats dynamics and the carbonate productions. So what we are very interested in is how the carbonate production in the certain habitats gonna turn into a geological fasces in the strata or stratigraphy. What we can do first is we can observe the changes of the habitats through bias, right? But the observation is very time biased. For example, if you are ecologists, what are we gonna do? We're probably gonna hire some people. They wear like equipments and they have a camera, and they're gonna just go down to observe all the habitats. Okay, so in the modern time, we can see okay, this place is hard ground, hard substrate. This place is seagrass meadow, and we also can record the individual carbonates producers inside the habitats. For example, on the top three panel, we can see like some corals in the on individual corals on the hard substrate, and on the bottom panel, three panels, soft substrates, basically the old sands. We can find some like echinoderms to put it. On the other end, we can also we can find some dynamics in the geological records, which is coarse. The timescale is over 1,000 years. But in this case, we can't see the dynamics. We can't even see the habitats. What we can see is just some carbonates from the course. As we can see in these panels, we don't need to understand what it is, but it's basically here we can see the yellowish places. After some interpretations, we probably know okay, this is from lagoon. We can maximum know it's probably roughly deposited in the lagoon, this kind of environment. We even don't know what kind of habitats in it. And the brownish red is probably from the reefs. But what kind of reefs, we also don't know. So in geological timescales, we can have longer time span of observation, but we can do only very rough. And the types of data is very different from what we can see from the course and previously on in the modern settings. So what we think is we probably need some data around like 100 years, and they are very important. They are not only allow us to extend the observational time period for the ecological studies. For example, before that, the ecologist can only observe the habitat dynamics around 10, 20 years because the cameras haven't been invented yet as back in 30 years, right? And also, it provides important time slices to better constrain how sediments produced in this kind of habitats are then turned into geological fascists in the stratigraphy. So how the actually the sediments produced in tens of the years gonna finally deposited as the rock stratigraphy that's recording millions of the years. So we think the time scale, the data for of the time scale with a time scale of around 100 years or multi-decade years is very important to bridge these two type of the data sets. So the aim of this study is we're gonna figure out the distribution of the modern habitats and the dynamics of the modern habitats and the production within it and how it turns into the geological fasces and the spatial and temporal distribution of the geological fasces. So by doing so, our first step is to understand the dynamics of the spatial heterogeneities of the habitats distributions. Um, we can use a lot of statistics and maps to show that kind of data. And after that, we're going to apply the Waters law, which is a spatial and temporal transition law to convert the spatial heterogeneity to temporal heterogeneity in the geological records. For guys you probably don't know, you don't know Waters law, I showed a figure on the right-hand side, which basically means what we see spatially adjacent is gonna eventually turns into like adjacent in vertical successions. So I get it is from somewhere in the textbook. Yeah. In terms of materials, luckily we get some very old vintage aerial photos from 1940s, which has been shown on the left-hand side. Um, and we're going to compare that to the modern satellite images on the right hand side. By doing so, we can get roughly around a time span of 80 years. We can't go into 100 years, but that's what we can go as far as we can. So 80 years, I think, which is already good enough. And the photos look like this. They are black and white, and they don't have RGB, but it allows uh, us to see some features and the fashion, or sorry, habitat distributions in these areas. So I chose one of the best, my favorite as area images over there, and we can because it has a lot of contrast. It has also have a lot of features over there. We can see a lot of things happening, and it's just like uh, very good. And we see a lot of habitats as well. I put 6 hearts on top of it to show how much love I like over here. So okay, in terms of how the vintage aerial images are obtained, I'm gonna use some animations to show here. So this is in the Bahamas. This is a place called Jordan's Key. So what I'm gonna do is in 1940s, I'm a British soldier, and I have uh, to figure out what the landscapes of the Central America and to better to have a war with the Germans. So we have some fixed wing planes, and I'm a soldier and I have a camera. What I'm gonna do is I'm gonna use my camera to shoot down the photos as the flight is going north. So oh sorry. So as here I shoot the first photo, and then I shoot the second one, the third one, fourth one, sixth one. So as flights going north, I covered this kind of place. I covered this area. So the final photo is obtained here. Sorry, I it's a little bit not on the right place, but this is how it's planned. And we're gonna choose two study areas. The first area is North Abacus, which is the B here. Sorry, the left big panel here. This is the Bahamas places. This is Bahamas. And the B, the first area we're gonna study is the B, which is North Abacus. And I zoom in a little bit, we can see. Um, And the second one I see is the Jotas Key, and it's situated in the north of the biggest island in the Bahamas, which is the Andros, and it's look like this. And we're gonna compare both the vintage photos and the modern satellite images in these two areas. Why we're gonna choose two areas? Because the geology is has the data in the geology study has a lot of noise. We don't want to say, okay, we just study one place and we just say, okay, it's universal. We have to study more than one place and to make sure our understanding and our observation is right. So we choose two areas. So the first area, sorry. So we first talk about the Jotaski. It's situated in the north side of Andros Island. So this place is tropical and it's have wet and dry season. It receives over 1,000 milliliters of the rain every year and some hurricanes every now and then. The temperature is very high in this area, and the wave and tide mainly come from the east side, so it's easterly area. Because this is situated in the bay, so the tide is relatively like magnified in this area. As we can see, there are a lot of like darker channel like thing. They're basically tide channels that indicates the tide is actually activated in these areas. This place is very young. It's only have the history of around 2,000 years and still rapidly growing, and makes one of the most interesting places in the Bahamas for sedimentologists. And we have a lot of literature about it, characterizing it and cores, whatever you name it. And the North Abacos, it has been less researched. As we can see, it's also influenced by wave and tide. And in terms of tide, we can see there's some sand aprons over here. It indicates these are basically deltas of the tide channels. um, and its face is open ocean, so it has also very strong wave. It has stronger wave than the previous Jotas Key place. There's one major differences between North Abacos and Jotas Key is North Abacos have some fringing reef islands, which is this. I use a laser to point them. They are fringing reefs, and they become over sea level and become islands. So it creates some lagoons between the real islands and the fringing reefs. So what I'm gonna do is interpret the vintage photos. I'm gonna use this as examples. So here, the very bright belts over here, they are basically some wood sandbars. Um, and on the right, these are lee sides of the bars, and so they are cemented and space stabilized by the microbiomes. And the very dark stuff here, this is islands, and some some sort of dark and cloudy stuff over here. They are seagrasses, and some like relatively bright but very smooth texture stuff. They're hard grounds, and they are something on the left bottom places, something like acne. They are patch reefs. So that's our interpretation. What we're gonna do is we first combine all the individual vintage photos into one big image using Metaship. This is a software developed by Agisoft, which is based in Russia, and I'm happy as I can still use it. And then we feed that into a software called Ecognition, which is developed by Trembo in Munich. And we're gonna conduct the ecological fascist interpretation and do some classification by using its built-in machine learning algorithms. And then we do some final georeferencing and manual editing comparison in ArcGIS. So here's the results. I'm gonna first show the results of the Jota ski. Don't worry. So on the left-hand side, this is the results of 1914. 1945. On the right hand side, this is the result of 2019, which is pretty close to our modern time. So each color represents each habitats. So okay, so light blue, they are hard bottom or hard ground. The yellowish stuff, they are wood sandbars. The greenish stuff, they are seagrass meadows. The black stuff, they are islands, which is above sea level, so they are terrestrial habitats. And the red stuff, they are sand that are um, cemented by the microbiomes. So we can see they are extending from north west to southeast along the shores. It's more, the shape of them sort of look like a belt, but it's much more complicated than a belt like distribution of the habitats. It's somewhere between the mosaics and the belts. So as we can see, during this almost 80 years time span, the seagrass actually gets much bigger visually. The islands also gets much bigger visually, and the sand seems, Awit sand seems gets smaller. So we do some statistics. We find that as, of course, the sand and hard ground has been gradually be replaced by the seagrass meadows. And three most important habitats we have found is hard ground sand with sand bars and the seagrass meadows. So they are important. And we find significant growth in the islands. So yes, despite the sea level is constantly rising, the island is still getting bigger. That's good to know. The reefs, patch reefs, despite they are very important, they only account for like 1% of the total area, and it's very hard to find the changes. So the second place we're gonna talk is North Abacus. Sorry, this is with less resolution because of my figures problem. But again, here the yellowish stuff they are active oid sands. The light blue stuff they are hard ground or hard bottom. The dark blue they are reefs, and the greenish stuff they are seagrass meadow. Um, and the black elongated stuff they are islands. So as we can see, the sand actually mainly just concentrated somewhere near the reefs, the fringing reefs, and there are a lot of heterogeneities on the outer shell of parts of the Abacus. And the sand is mainly distributed in the delta alpines, like here. And in this comparison, it's very hard for us to know, okay, how each habitat is changing. So we do the statistics and we find that in this region, the seagrass and hard ground has been gradually uh, transferred into active weed sandbars. And islands, of course, is also growing in these places. So okay, so here's the results of the comparison. So in both area, the islands are increasing despite the sea level is rising. So which means that we actually provide more sediments to build the islands than the accommodation created by the sea level rising. And also in the both cases, the hard ground is shrinking. So this probably also indicates that the sediments is so much and it's the hard ground is turns into the active accumulation area instead of hard ground, and it's like not accumulating anything. And in the geodesy, because we have microbiomes and the macroalgae cementing sands, and in both of them are increased in the geodesy, but not too much. And the seagrass meadow, this is a little bit weird. Like they increase in the geodesy, but they decrease in the North Abacus. So this is not like universal. So it's case by case, it's different. The first question we have to address is this change just like short term or long term? So we know like interannual seasonal changes or hurricanes. What we say before, what we just say at the beginning of the talk is all of this gonna change the dynamics of the or the distribution of the habitats. So what we're gonna do is, okay, we find there's a huge hurricane Andrew in 2016 just destroyed the north of the Bahamas. So we just choose one satellite images before the hurricane, which is on the left hand side, and the one after hurricane, which is on the right hand side. And we choose like two small zooming panels to compare the pre and post hurricane distribution of the habitats. So our results is okay. So despite we have very big hurricane, the distribution of the habitats is not changing that much, especially in panel C and D. The seagrass are still there. The sand is also still there. They're just not changing. There are slightly changes in panel E and F, but overall, the seagrass patches and the corals, which are these acnes, they're not moving. They're still there. There are some sand bars has been activated, as we can see here, indicated by the uh, white arrows. They has been activated a little bit, but I mean before that they are also just sand, but very lightly covered by seagrasses. So our conclusion is after like catastrophic like very big hurricanes, the distribution of the habitats doesn't change that much. So it's not so. I have to say probably very likely our changes of the habitats in our observation of 80 years is very likely to be a long-term change, not small or short-term changes. So the first thing is we have to understand um, uh, the dynamics of the habitats, right? That's our first aim. We have to do some statistics about the habitat patches. Um, First, we have to do the statistics based on the size of the patches. And the top two panels here, they are the results of the Geodesy, and the bottom two panels, they are the results of the North Abacus. So in all four panels, the x-axis is log of the patch size. The y-axis is a number in each bin, so it's a histogram. The NP means number of patches. So how many patches of habitats in this area? The MET is median size, and MPA is mean size. So MET and mean, so median and mean or average. So in the geodesy, we can see that the seagrass is the overall total seagrass coverage is increasing in the geodesy. So the number of patches is increasing, but the medium size and the average size of the patch decreased rapidly. So this means that in an increasing scenario, the number is increasing, but the size, medium or average size, is decreasing. This makes this area is more fragmented. So the habitat is more fragmented. Why that is probably because we have a lot of new patches has been generated in this area, and these new patches, for example, seagrass patches, they are still very small. So this makes it looks more fragmented, but just because we have more smaller seagrass patches added to this area. So for the abacus, this is completely different. So in abacus, seagrass coverage is decreasing, and we can see the distribution of the seagrass patches in 1945 is more like log normal distribution, but in the modern it's more like a bimodal. So it has two peaks. The number of the patches decreased by 2/3. That's a very big change. But the medium didn't change that much, and the mean size of the patches increased by 30%. So that's very different. Um, it gets actually less fragmented. Why? That's because smaller patches get erased during this time. So we do another analysis. So on the x-axis, this is still the log of the area of the patches of the seagrasses. On the right, on the y-axis, this is the change proportion. So 300 means that's the number of the patches in this area. Uh, the number of patches in this bin in this area has been increased by three times. Three times. So as we can see, like smaller patches, like in the left hand side of the figure, it actually have more higher proportion of the changes. And if we get into the intermediate, like bigger sizes, the changes are smaller. And if we go to the very big patches, this loses statistic meaning because we have very little numbers of them. We only have like 1, 2, 3 in each being, like 1 or 2 or 3 numbers in each being. So they lose the statistical meanings. Well, that what I mean is, considering the statistical meaning, it's like smaller patches are more subjected to the changes. So no matter it's like the total area of the seagrass is increasing or shrinking, the small patches are less persistent. They are very subjected to changes. They can like go vanished or get generated very rapid. So okay, we can use this kind of data to extend the habitats informations to the sedimentology and stratigraphy side. So what we first have to do is to do the source to sink calculation. What we have observed is islands is growing rapidly in these two areas. And we know the island's growth needs a lot of oil sands. So we are thinking that oil sands probably come from the nearby sand shores, which is represented by the yellow belts over here. So we're gonna test like to do a budget test, budget balance calculation to test. Okay, um, is production in this sand shores enough for the island's growth? So we first calculate how much sand can be produced in this sand shore by assuming some production rates that we get from the literatures. We calculate the production rates times area and the times the time, and we can get how much has been produced in the oil sand shores. And we also calculate the gross coverage, the area that's gained by the islands, and we can calculate how much sand it actually needs. So the source to sink calculation suggested that the island's growth actually consumed 10% to 100% of sand actually produced in the shore, depending on the production rates we have chosen. So which means that the sands that oil sand that's produced in the sand shores probably very likely not situated in situ. They're moved to other places. That can sort of explain why, if we go to monitor or to measure the accumulation rates of the carbonate platform, we see that the long term accumulation rates, like long term, like 1,000 year, 100 year, or 1,000,000 year, long term accumulation rates is much lower than the short term accumulation rate, because what has been produced is transported to somewhere else, and this is not small proportion, and it's very very big proportion. And then what we're gonna do is we have to track the patches of the habitats. We use a seagrass meadow as example again here. So on the left hand side, this is the patches distribution of the 1945. On the right hand side, this is the patches in 2019. So the same patch, they share the same color code. Here, this is a pink. So pink is expanding and move a little bit right, eastwards. And this is the biggest patch. This is the blue one, and the blue one expand a little bit and migrate a little bit east side. And there are some small patches. And we use our package called Plat Tracker, and it helps us to track the changes. And then we do statistics, and we find that the centroid of these patches mainly have two or four direction. One is perpendicular to shoreline, which is like southwest to northeast, which means that the patches are expanding perpendicular to the shore, and there are some small changes as well along the shores. So we basically either along the shores or perpendicular to the shores. So for the oil sandbars, again, the same color code is the same patch, and it has similar directions compared to the seagrasses. It's either going perpendicular to the shoreline or along the shoreline. So okay, so centroids of the seagrasses. Okay, so we can use this kind of data to do something interesting. Our aim is to use this observations of 100 years to try to convert that into the stratigraphy. So we based on Waters law. So what we're going to do is we employ a cabinet architecture model called Stacker that has been written by Peter Burgess, our collaborators from University of Liverpool. And this is a forward cabinet models. So it's basically assume there are some patches in the shallow marine sea, and they just migrating constantly in the space, and in each time step they're gonna grow a little bit, they're gonna accumulate some carbonates. So with time it's moved to a new place and accumulate some. It's in the new time and over and until it creates a thick uh, a very thick carbonate sediments. So in our case, we use a random walk of the fascist patch. So it basically means that the patch migrating is more like random, randomly migrating it, but the patch size and the migration direction and the migration rates are coming from our observation of the Bahamas. So we use this kind of data to try to build a virtual stratigraphy. So in this case, the red is wheat sands, the yellow is seagrass meadow, and the green is hard grounds. Sorry, I messed up the color code, but that's what we do. Here is the results. On the left, both top left top panel, this is a Wheeler diagram, which means that at what location, um, what kind of fasces, which is represented by each color code, gonna be deposited or not in a certain time slice. So y-axis is a time. So which means that at this place, uh, my cursor here, my highlight here basically means at a place at 5 kilometers away from the shoreline and at geological time of zero point 0.2 million years, there are some yellowish, which is what's the name? The seagrass carbonates deposited in this area. So this is a Wheeler diagram. It allows us to know the spatial and the and temporal distribution of the carbonate accumulation. So the the bottom left panel. This is a cross section of the carbonate platform, and you can see it's mainly dominated by wheat sands, which is orange, and some yellow, which is the seagrass middle, which is finer grains. Um, a little bit of greenish, which are hard ground. So if we get the cores along the shores, we can see it's mainly represented by a big chunk of wheat sands and punctuated by some fine grains that's produced by seagrass meadow. And we even couldn't see any kind of hard ground because hard grounds don't produce that much of things. So this makes sense. So how it compares to the real data? So we actually get some cross sections that has been published before in I think in 1970s by Harris in Georgia's Key. So we're gonna compare virtually right now. We're gonna do more statistically in the future. So here the big blobs over here, the wheat sand, and the smaller grains, they are finer grains that's produced by the seagrasses. So I would say it's actually looks pretty similar. So both of them look like a very chunky, like a big chunk of of wood sand and punctuated by like fine grain sediments that's produced by seagrass meadow. Um, yeah, I think that's our results over here. So the conclusion. The first conclusion is the first takeaway message is sand actually produced in the shores. They are transported to other regions. That's why the long-term accumulation rates is much smaller than short-term accumulation rates. The second is for the ecological studies, the small habitat patches they are very subjected to extensions, like they are changing rapidly than the larger ones. And I'm gonna leave open questions in here. Based on the stacker model results, do you think the fact and the results of the Bahamas observations, do you think the fascist distribution are more like mosaic like or the belt like? I think that's it. Thank you so much.
Thank you, Shiani. This was a great talk, and I think the audience is also sharing the same sentiment. I would like to remind our audience that you can ask your questions now either by unmuting yourself, or by raising your hand, or by chatting with our questions at Paleoperk's host, who is Nina, for today, or you can just directly put your questions in the chat. But we already have some questions. So we will uh, go with that. So our first question is an anonymous question, and it's asking, it's saying, very cool way of using old data. Are such high quality vintage aerial photographs something that could be used to study other areas in a similar way? Or is this something that is unique to Bahamas?
Oh, we also have some. Yes, there are some vintage photos. Well, for our project, we mainly just concentrated in the Bahamas. But yes, of course, we have a lot more vintage photos in other areas, including West Australia, as far as I know, because I go to Miami to scan them, and we scanned both Central America. Uh, including Bahamas, Turks and Caicos, Turks and Caicos, this area, and western side of Australia. So yes, we have more. But for Australian photos, I'm not quite sure about the year it has been taken. So yes, but it's
So,
definitely vintage, very old.
yeah, I think there is a related question. What is the approximate resolution of features you can study using this photo based approach?
Oh, okay. So because this is analog photo, so it's actually, in theory, the resolution is unlimited. It's basically the resolution is like the chemical particles. That's the resolution, like probably molecular size. But we have to scan it with certain pixel, right? I'm now using 600 dpi, but you can definitely do more. And if you use 600, is roughly less than 1 meters. The resolution is so it's very high quality. It's roughly similar to what we can obtain using very good commercial satellite images nowadays. So the resolution is roughly similar. That's very good. Yeah,
Wow, that's very fascinating.
yeah,
Um,
it's very good. Very nice, very good vintage archives stored somewhere in Miami. Yeah.
yeah. So we have another question which is asking, which environments do you think are most susceptible to misclassification, and why?
Sorry, to subjected to what? Sorry, can I ask?
Which environments do you think are more susceptible to misclassification?
Okay. To misclassifications, I think definitely. It depends. I think in geodeski, it's the reefs and the macroalgae area, because macroalgae, they are very from the satellite images, they look very similar to seagrass. Actually, it's just like seagrass is a little bit more cloudier, and macroalgae is more like more rounded shape. So that's only differences we can get. And the reef, of course, they're so small, and there are a lot of them. They're just like bacteria. They're everywhere. So it's very difficult to specify them, and it's subjected to a lot of errors. I have to say that. So that's why at this stage I didn't include the reefs over here in the interpret sorry in the discussions, because we know there are a lot of errors over here. Yeah.
Thank you for that answer. We have another question which is asking, do you think there is any human contribution to the observed changes in the environments in the past 80 years, such as the
Oh,
island growth, or is it all natural?
uh, well, the thing is, like, we choose two areas that have no people habitated in this area. So if we go south to like Andros Island, or goes to the capital of the Bahamas, yes, of course, when we actually have some observations that in like hotel regions, and they have like all pipes like draining all the like shit waters, like dirty waters into the sea, and we can see seagrass is like booming because they just like, okay, a lot of phosphorus, I like it. But in our regions, like Jotaski has nobody inhabited in this area, and the Nos Abacos also, they don't have too many people over there, so we think it's mainly natural, but we can't exclude the indirect changes in area. For example, the dredging of the sea beds, like some uh, fishermen, they just like to fishing in this area, and they use like a lot of instrument or whatever stuff to destroy the seabed. We don't know. And of course, indirectly, sea level is rising because of global warming, and this gonna, of course, increase the increase the water depths in this area, and of course, also gonna change the places indirectly. So directly, I would say direct anthropologic change influences. I would say probably very small, but we don't have evidence to say, okay, it's very small. It's just like my illusion. It's small. We deliberately change this place because in habitat, it's not habitat. Sorry, and indirect influences. There are so many, and I would say yes.
Thank you. That's definitely, it's very complicated to talk about the anthropogenic influence. Um, So we have another question. Interesting work. First, they're saying, so on timescales of 100 years, are some of the facies shift preserved in the geological record, or is it still just moving around of sediment without burial or and preservation? That only happens over 1,000-year timescales or longer. This question, they're asking this question because the time scale of the stacker wheeler diagram seems to be close to 1,000 years.
This one.
Yeah.
The time step of this is actually I think 200 years, not 1,000 years.
Okay. Okay.
Yeah. So
Cool.
I just use it's still not like we, I know we are observing at 80 years, but it's, I mean, it's at the same scale, so 80 to 100, not that bad. And I also, I can change it to 100 to make it better. So I just directly use the data over there to feed into the stacker. uh, uh, I didn't extrapolate or interpolate anything. I just directly use the data over there to feed into a stacker. Yeah.
Got it.
I'm not sure whether I understand the questions correctly. If not, please let me know.
Yes, I think you definitely answered this question.
Yeah.
We have another anonymous question. Have you looked at the history of storms or storm tracks in these two different locations over this time interval?
Yes, we have looked at the records of the storms, and of course, if you read the papers in Georgia Ski, there's a paper written by Mitch Harris. with like a Georgia ski guy who spends his career in understanding this area and produce a lot of nice papers. He actually thinks that the islands accumulation of the islands or growth of islands is because of the repeated hurricanes, because the hurricanes are so strong and they created a lot of strong waves and just to push all the sands from the old sand shores onto the islands. So it's islands because of the hurricanes. And we actually also we have like a summarize the hurricane a history of these regions. It's mainly just every 10 years we're gonna have a hurricanes, but before that, because we haven't invented or created meteorology 150 years ago, right? So before that we don't have. But recent 100 years, yes, I think we have some history of the hurricane data, but uh, but if we don't have the satellite images to constrain the changes, it's we just know we have hurricanes, but we don't know what the changes. So I just choose one like hurricane as an example to say, okay, uh, it's not changing that much. Yeah, that's our logic. Yeah. Yeah, we definitely. So in summary, yeah, we summarized the historic storms events, but in terms of the how they're gonna influence the habitat distributions, I don't know. We just choose the most one of the most recent one to show that it's probably not changing the distribution of the habitats that much. Yeah,
Cool. I think this will be our last question for the session. So fascinating talk again, and more of a philosophical question. Do we have to choose between belt versus mosaic fishes? Can it just
actually,
be both?
sorry, please go ahead.
Can it just be both?
Perfectly right. That's what I'm thinking, to be honest. Um, if you see the if we like if now we are looking at this scale, I mean spatial scale, but if we like extend the scale, the belts actually are mosaics. So it depends on the scales. So if we like if for example if we mapped all over the Bahamas, we just see okay the belts in the Jota ski are actually just a small patch in this area. And also, if even if in this spatial scale, we can see actually there are a lot of like the I would say actually the belt is more like amalgamated by smaller patches. So you're perfectly right. Is actually it's not one or zero question. It's not like a yes or no question. It's like actually somewhere in the middle. It's like a gray zone. So definitely we are somewhere in the middle. So it's I would say okay. So the cabinet producers, why they are more or less like a belts like a thing is because their niches are built like um, distributed, but their niche is built like distributed. Doesn't mean they're gonna populates all over the belt, right? They can just like choose a few areas to live, and in that case, they are more like the patches. So, what I mean is, yes, of course, it's somewhere in the middle, and we don't know how to better characterize them. That's why I leave the open question over there. Is like, okay, a belt model definitely not right. Patch model probably also not right, but we know it's somewhere in the middle. But like where to set the boundary, where to set the threshold? Is it more like built like, or is it more like the patch mosaic like? So yeah, that's the thing.
Thank you, Xianyi. I think that was plentiful questions, and I would like to thank our audience for joining us today. Very nice to see you, and you can join us on 11th November at 10 a.m. UTC. Please note the unique time from our usual 16 p.m. UTC. And we will be joined by Viplop Rajuvkar from the Tongjing University, Shanghai, China. Um, and up next is Tea Time, which is an informal conversation with our today's speaker. And before that, we have a quick 2 minute break so that you can get up, stretch your legs, and come back with your paleo pets if you have any.